Okay, so today will be kind of a relaxed day, so let's just do some Olympiad geometries. Yeah, might as well talk about radical axis. So let's just quickly So let's just quickly talk about power of a point, and then the discussion will lead us to radical axis. So, if you recall, or I'm sure everyone knows that, if you have a point P and a circle O, then you can define what's called the power of the point. So like if you have two lines through P that pass through the circle omega with center O, then you can prove with similar triangles that like PA times PB is PC times PD. And this is true because of angle-angle similarity. You can draw in these lines and see these two intersect the same arc. This is a shared angle between the two triangles. So PCB is similar to PAD. And then you cross multiply the ratios and you'll get this. So PA to PD is PC to PB. Okay, so this works even if P is inside the circle. So if you have the same thing where one line through P intersects it at A and B, and another line through P intersects it at like C and D, then you'll have the same similar triangle configuration of some sort where these two are equal and these are vertical angles. So PCA similar to PBBD. And we'll definitely do some harder stuff today, but I just want to make sure we do everything rigorously from the ground up. So that means that by angle we have these similar triangles, and so PC to PA is PB to PD, and then we have the exact same relationship that we had before. This time, even though P is inside the circle, you still have PA. So, the way to remember is P to the first line of intersection and P to the other intersection point along the same line is P to the second line's intersection with P to the second line's second intersection with the circle. The same thing happened here. So yeah, that's just basic power of a point. So this quantity we call the power of P. So I'll just say power of P with respect to the circle omega with center O. So, if we just look at the first diagram again, so, I can draw any line through P, and the quantity, if this is like A1, B1, A5, B5, B4, A4, and so on, B3, B2, P to AI times P to BI is constant for all I, right? So this is a constant, and we call that constant the power of the point P with respect to the circle omega. So you might wonder, okay, so what's the difference between the power? So this is like an invariant, right? No matter as long as P is the, well, first let's get a formula for it, right? So let's get the formula for the power of a point. So there's two ways we can get the formula. The two ways will prove the Pythagorean theorem combined. But if we have this point P, and let's just take the line through the center of the circle, right? So here, let's say this is R and this is D, the distance from the center to P. So you can see that, PA times PB is just like D minus R, D plus R multiplied together. So that's D squared minus R squared. The other way you can see this is if you take the tangent point, like if you take a line that's tangent to the circle this time, then the two intersection points are the same. So A equals B, because the line intersects at the tangent point twice, you can think, because it's a tangent. And then here, we'll get that the power is the length of PA times PB, and A and B are the same points. So that would just be, this is a right triangle with hypotenuse D and leg R. So this is just square root of D squared minus R squared times square root of D squared minus R squared. So yeah, we get the same thing either way. Oh, there, I forgot a squared there. Yeah, thanks. So yeah, so these two ways to find the power of point P with respect to a circle, you can combine them to say that it proves power of a point. And the only fact we used was that we used angle-angle similarity in the similar triangles thing. So if you combine these two proofs of what the expression for the power of a point is with respect to D, the distance between O and P, and R, the radius of the circle, you get a proof of the Pythagorean theorem from similar triangles. Because power of point, uses things similar of triangles. It's built on similar triangles. Okay, so that's if P is outside the circle. If P is inside the circle, let's see what the power is, right? So one way we could define the power is the same as we did before, right? So you have P, you have any line through, the line through P and the center O of the circle, and let's call it POD again. This time, this is R. Yeah. So you might think, this will just be like, let's make it A and B. So the power of a point P is PA times PB. So looking at here, this is R, this is D. So you might think it's like D minus R and D plus R, which is D squared minus R squared. Oh, sorry. Sorry, this is R minus D, sorry, and R plus D. So it's R squared minus D squared. But now we have two different expressions, right, for the power of a point, depending on whether it's outside the circle or inside the circle. So we might not want this to happen because let's say this is a function of D, right? So power point. So this is a function of D with respect to the circle omega. So, this is a quadratic with like x, y intercept negative R squared, right? But when it becomes negative, we kind of flip it over, but we don't want that, right? Because now we have this weird function where it's not differentiable at this point and not differentiable at that point. So it's kind of a weird function if we do a different function for when the distance D is negative, meaning D is inside the circle. So yeah, like Alan is saying, we should use directed lengths. So instead of making it like PA times PB, let's just make it like, let's say there's a direction given to the length PA and a direction given to the length PB. So if we look at the original example, PA points the same direction as PB. So if they're pointing the same direction, it's like plus and plus or negative and negative. So the power will be a positive number. If P is inside the circle, now PA as a vector points in the opposite direction as PB. So now we have to assign one of the directed lengths a negative sign for its like the value of its length. We'll give like a positive direction to one of the lengths and a negative assignment to the length here, since we'll just say, oh, this is positive length R minus D. This is negative length R plus D from the value of P, which is like 0 or something. So yeah, we'll actually just say it's D squared minus. So then the directed length would be r minus d, and then it would be like negative d minus r for the other length, which should work out to be the negative of that. So it's d squared minus r squared again. So we do in fact have that the power is a differentiable function that is a quadratic, and it just happens to be negative, which is really weird, when it's inside the circle. But it actually makes things nicer if you allow the power of a point to be negative with respect to the circle. So one more observation is that the power is invariant if the point P is a certain distance away from the center of the circle. So all points on the dotted line, if they're d away from the center O, then they have the same power with respect to the circle omega, because you can always draw the line through the center and P. And if d is constant, then the calculation here is constant for all points P along the dotted circle. Same thing outside the circle. If you take any point d2 away from the center O, those all points on the second dotted circle will also have the same power with respect to the circle. So the power only depends on the radius of the circle and how far our point in consideration is from the center of the circle. And we can see that here. This is power with respect to the circle of a point P. So you should probably write it like OP squared, the distance from the center to the point, minus the radius squared of the circle, omega. Okay, so then that's the notion of the power of a point. And now you know why, so power of a point, it can refer to the power of point theorem, which is that the power is constant regardless of the line you take through the point P. It can also refer to the quantity, the power of the point with respect to a given circle with a given radius. As long as your point is a given distance away from the center, it's well defined. So then the question is, what if you have two circles, right? Yeah, if you have two circles, there are three configurations we should consider. So the question is, so let me just draw the configurations. And they can also be tangent. The question is, what is the set of all points that are have the same power with respect to both circles? So if we call the circles omega 1 and omega 2, then then it turns out we can find the locus. So let me just type this out. Is the locus points with the same power with respect to two different circles. Let's say non-concentric circles. Two different non-concentric circles in the plane. I guess it could be in 3D space too, but we won't worry about that for now. So yeah. So, I guess there are some other configurations, like this is also a configuration, but we'll just say this is non-intersecting, just like that's not intersecting. So anyways, so we have those four configurations, I guess, 0, 1, or 2 intersection points. So, the way to prove this, the most easiest is just coordinates. So this is one of the rare instances where coordinates give the easiest proof. So let's say we have one circle with radius A, and it's centered at the origin. And then you have the other circle. So we orient the coordinate axis so that this will have radius B. And we'll just say this is at C, 0 or something. Now let's make this M, 0. There we go. So, let's say we have an arbitrary point P, right? We want to find when is the power of a point with respect to that circle the same as the power of the point with respect to that circle? So power P with respect to omega 1, so let's call this omega 1 and omega 2, is the same as power P with respect to omega 2. So, using our formula from above, that just means, like, let's call this O and O2, O1 and O2. So O1's P squared minus, let's just call it R1 instead of A. So R1 is the first radius equals O2 P squared minus R2 squared, right? So that's our condition for P having the same power with respect to both circles. And then maybe this just has coordinates like X, Y, or something. Then we just use the, we just coordinates, plug in the coordinates. So here, this is X, this is Y. So that's OP squared minus R1 squared is a constant. And then here we just have like Y squared plus M minus X squared or something. That's O2P squared minus R2 squared. So then if we expand all this stuff out, a lot of stuff will cancel. So, that goes away, that goes away, that goes away, that goes away. And then, hang on, let's see. Yeah, so we have just one variable X, right? The Y's all went away. So if we solve for X, we'll have something like so that's the X coordinate of all points in our locus. And then we can notice here, M, what is that? That's just a constant, right? This is just the distance between O1 and O2. The radii are constants because these two circles have given radii. And this is a constant as well. So yeah, so that means this is just a straight line with X coordinate, whatever the heck this expression is. So this is X equals that thing minus that thing plus that thing over 2 times M. And this is a constant because all the variables in that expression are constants. So the locus of all points with the same power with respect to two circles is just a straight line that is perpendicular to the line joining the centers of the circles. So let's just type that out. With the same power is a straight line perpendicular to the segment joining the centers. So this line, if the two circles are like not inside each other, is in between it's like the way I drew it here. It's like right here, the red dotted line that's half black. If the two circles are like this, so if the two circles are like this, then the radical axis is kind of like that. It's still perpendicular to O1, O2. It's just that it looks a little different because it's like a different configuration, sort of. What if the two circles intersect, right? Then where is that radical axis? Let's say, it's O1, O2, and they intersect at X and Y. Yeah, so how many points determine a line, right? We know that the locus of points that have the same power to both circles is a line. So we can just find certain points on that locus to identify exactly where the line is oriented and located. So X has the same power with respect to the circles, right? Its power is 0. Like before, I forgot to mention that we mentioned the case when P is on and outside the circle. What if, P is inside or outside the circle? If P is on the circle, then P is the same point as A, and the other point is B. So here, PA times PB is just 0 times PB. It's just 0. So points on the circle have, power 0. This is R squared because R equals D minus R squared. Using our formula D squared minus R squared, or, yeah. So, okay. So that would correspond to these 2 points on our graph. So that means the radical axis here is the straight line passing through the intersections of the circles. If the 2 circles are tangent, it's it's also perpendicular to the line joining the centers, and it goes through their intersection point, which is the tangent point between the 2 circles, which is both intersection points of the 2 circles, if you consider the 2 intersection points to be the same point. So yeah, so we have those 4 configurations. I'll just draw this one in again. Okay, so now I guess we should talk about like the, oh, I didn't make this document very long. Okay. So let's just talk about radical axis theorem. So now what happens if we have 3 circles, right? So we're going to prove that the pairwise radical axis of 2 of the 3 circles, all 3 of them intersect at the same point. And that point's called the radical center of the 3 circles. So, there are some different configurations for how the circles could be. Maybe none of them intersect, maybe some of them intersect. So yeah, if you intersect 2 of the radical axes, like let's say omega-1 and omega-2, you intersect their radical axis, and omega-1 and omega-3, you intersect their radical axis, then all points on the green line, they have the same power with respect to omega-1 and omega-3, right? So for all points P, this is true. For all P on radical axis of omega-1, omega-3, that's true. And for all points, P, Q on the radical axis of omega-1 and omega-2, their power with respect to the 2 circles is the same. So that means, what about their intersection point now, right? So the intersection of the 2 radical axes, what must be true about that? Let's call this like X. So X is on both radical axes. So not only is its power with respect to omega-1 and omega-2 the same, because it's on the blue line, also its power with respect to omega-1 and omega-3 are the same. So in fact, we get that its power with respect to all 3 circles is the same. But if the power with respect to omega-3 and omega-2 are the same, then by definition, it also lies on the radical axis of the 2nd and 3rd circles, omega-2 and omega-3. So it has to lie on the red line. So you'll never have 3 radical axes, of 3 circles, taking them pairwise that, looks like this. They can never look like that, or they intersect in a triangle. These 3 points should always be a single point. The 3 lines should always concur because of what I just said. Yeah, so today we're just talking about some radical axis stuff and maybe some other Olympiad geometry stuff. So you can look at the recording if you arrived late. Okay, so with that in mind, let's look at some problems. So uh, so let's just look at a super old USAML problem. And then we'll look at okay, this is good enough for now. So maybe we'll just talk through them together. So let's look at the 1991. So you have a triangle. So this is for the first problem. Let's just label it. And then let's see. It says the circle with diameter AB intersects the altitude of C at two different points. So, what's a special point that, or what are some special points that this circle should intersect? Maybe let's draw it a bit better. Right. For instance, if I label these 2 points, what should those 2 points be in the triangle? If AB, is the diameter of this circle. Well, we might as well connect this line and this line. So because this is a diameter, this is a 180-degree arc. So this angle, AL, I'll call it A prime B, is half of 180. So it's 90, right? So that's the altitude. So this point, the intersection of the circle with diameter AB with BC, it intersects at the foot of the altitude from A to BC. Similarly, this is also a 90-degree angle. So B to B prime is, well, that's, the foot, that's an altitude. Okay. So then, oh, my diagram's not very good because the 3 altitudes should intersect. So let's just fudge the diagram so that the 3 altitudes intersect. So this should be the altitude from C. It should intersect that, right? And then let's just move our label again. So, if this ever happens to you, you can just do what I did because you won't draw the diagram perfect the first time, right? Or you can just redraw it, which is probably a good idea as well. Okay, so then you have diameter with AC as the diameter, a circle with diameter AC intersects. So let's just. So this will also pass through A prime, like by the same reasoning as before, as center right there. And it should actually pass through that line. That point, right? So it should pass through both this foot of altitude and that foot of the altitude by the reasons we said earlier. Okay. So yeah. So then it says it intersects the altitude B prime and its extensions at P and Q. So this is P and Q. Let's just do it in green again. So P and Q. Okay, so prove that M and PQ are concyclic. So yeah, can anyone see why this is true? Someone is multitasking. Okay, that's fine. Yeah, so I'll let you guys think about it for a bit more. So think back to what we just learned. Like, what's the radical axis of two of the circles, right? Okay, yeah. So someone said it earlier. This is the radical axis of the red and blue circles. It's the altitude of from A to BC. Yeah, right. So, we don't have to use the theorem we just proved, but let's just think about some things, right? So we should take the power of a certain point with respect to these two circles. Which point might be a good point to take a power of with respect to both circles? Take power, probably A. Well, if we take A has what power with respect to the blue circle? Yeah, it has 0 power to both circles, so maybe not the best choice. So the intersection of MN and PQ? Yeah. So what is the intersection of MN and PQ? Because we want to show that there exists some circle that passes through these 4 points. We don't know if it's actually true or exists yet. So Sonak says orthocenter. Yeah. So the intersection of MN and PQ is the same as the intersection of the altitude from C and the altitude from B, right? C prime and B prime. So that's H, the orthocenter. So let's just use power of a point on this, right? So, on the one hand, what is, let's just do the common chord, right? So HA times HA prime. Give me an expression that this equals. What is HA times AH prime, which are, these 2 points with respect to the orthocenter? So let's see, it equals HQ. Yeah, so on the one hand, it equals HM times HN, right? So we can see this by looking at the blue circle. This line times this line equals this line times that line by power of a point on the blue circle. On the other hand, if we look at the red circle, HA times HA prime is just HP times HQ, right? So that's power of this point of H with respect to red circle. Oh, hey, what is this? What does these two being equal say? Well, we didn't prove the converse of power of a point, the regular old power of a point theorem. But if you just have two sticks and they intersect or something, HP times HQ and HM times HN, if you have the power of a point condition, then you can, just divide, uncross multiply, divide through and use similar, so then you have side angle side, right? HP times HQ equals HM times HN. Divide through, you get HP over HM equals HN over HQ. So HP over AM, that's that divided by I mean, that divided by that is the same as hn over hq. Because these are vertical angles by side angle side similarity, these two triangles are the same, are similar. So that means these two angles are the same, which means that these 4 points have to be concyclic by the converse of the inscribed angle theorem thingy. So yeah, and you know, maybe we should prove that, but yeah, that's how you can show using only basic principles. So yeah, so that means that you know, this implies that M and PQ are cyclic. So M and PQ are cyclic. Okay. So let's see. Maybe I'll just erase this and drag this to another point on the PDF. So so let's see. You have 2 points. Blah, 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 blah. Yeah, let's not do it like this. It's just like it's good enough. Oh, okay. This is a slightly different. Okay, that's fine. Sure. Maybe, you know, there could be a slightly different configuration where they're like this, but let's not worry about that. It shouldn't really matter. So yeah, anyone have any thoughts? So we're given that PQRS are concyclic this time. Given cyclic. So let's just draw the circle through them. You know, supposedly the problem tells us these are cyclic. So it looks like a bad circle, but oh well. So let's see, y-axis, the radical axis. Yeah, of the two first circles, the omega 1 and omega 2, yeah. So maybe I should draw like, get a better diagram. I'm just gonna copy this over from Evan's handout. So we want to prove that the center of the third circle also lies on XY. Probably connect O1S and O1S O2R. Maybe. Yeah, I mean, we could connect these. I'm not sure if it's super helpful, but we could. So draw the circumcircle of SPRQ. So yeah, that's the green circle here. And Alan says radical center. Yeah, so it looks like we might have something with radical center here, right? Or at least radical axis, right? So the interesting thing here is that we have to use that, the fact, like what's interesting about this problem that's not in the original radical axis theorem statement? Like what's unique about the problem? We're trying to prove a center lies on a radical axis instead of a consequence. Well, okay, but like what's a given information that's different than a radical axis statement? We know PQRS is already cyclic. Well, yeah, but that's part of the radical axis statement. What's like an actual difference between this and the general diagram of three circles? So you could just randomly draw three circles, right? And something about this diagram is slightly different than the general configuration. One center lies on the radical axis of the other two. Yeah, exactly. So, you know, yeah, all centers lie on each radical axis, right? We're told that this O1, the center of the omega one, it lies on, well, the line through it, it passes, you know, PQ, that's the radical center of the green circle and the blue circle, or omega 2, right? So O1 lies on the radical center of this circle omega and omega 2. Same for O2, right? It lies on the radical axis of the other two circles, omega 1 and omega. So that's the unique thing. So we have to use that, right? We have to use this unique piece of information that's like, you know, more info than the general, you know, the usual radical axis statement. So let's use that. So O1 on radical axis of omega 2. So what does that say about O1, right? So power of O1 equals power O1 with respect to like omega and omega 2. So maybe we should like give names to the radii, right? Like R, R1 and R2. This is R, this is R1, this is R2. So so what is the power of O1 with respect to omega, I guess? So this one, on the one hand, it equals, can you express it in terms of the line segments and R, R1, or R2? So, well, it's the distance from this point to the center of the circle. So O10 squared minus, you know, R squared. On the other hand, this is also O1, O2 squared minus R2 squared, right? Because we just applied the formula we had. Okay, so now we should use the other information, which is that O2, you know, similarly lies on radical axis of omega 1 omega. Oh, this should be just omega. So, power O2 equals power O2, which is like this is for omega 1. This is for omega, I guess. Let's just make this omega, and this is for omega 1. So then we have the same thing. O1 O squared minus R squared equals oh, sorry, this time it's with respect to omega 2, right? So we should put a 2 here, and this is respect to 1. And this is R1 squared. This is the center of the second circle to center. Oh, sorry, let's see. So let's make that omega. So this is this and this. There we go. I can't read my own handwriting since I keep crossing out instead of erasing. So then O1, this squared minus this squared. Okay. So yeah, what should we do with these two expressions now? Subtract? Yeah, let's try subtracting. They both have an R squared, so maybe we want to cancel that out, right? We wanted to prove that, remember, we wanted to prove that O, the center of the third circle, omega, it lies on the radical axis of the first two, right? So we want to eliminate all information about O and only get information about O1 and omega 1 and omega 2, the first two circles. So if we subtract 1, subtract 2, we'll just have and then these two are the same as well. So we'll just have, okay, so then how can I rearrange this to be something that we're used to? Oh, hang on. We did, no, this should be negative, this should be positive, right? Because I did 1 subtract equation 2. So let's put all the terms with 1 on one side, right? Goes O2 minus R2 squared. So what does this say? Do you guys recognize what this expression is? Yeah, so which power expression is this? Yeah, this is power of a point. It's the power of point, what point with respect to what circle though? The power respect to point O of omega 1, yeah. Yeah, so yeah, we get exactly what we wanted, right? This is similarly the power of O with respect to omega 2. So power O with respect to omega 1 equals power O with respect to omega 2. Therefore, yeah, so therefore O lies on XY. That's exactly right. So now we know that the third circle, its center O lies on the radical axis of the first two circles, omega 1 and omega 2, because that's what our equation said. The radical axis is if and only if, like if the powers are equal, then you're on the radical axis by the definition of the locus of the radical axis. And yeah. So we're using the fact that the locus happens to be a straight line through X and Y. Great. I don't know if there are any like special cases we need to worry about. So there is one configuration where like there is no radical axis, or the radical axis is a point at infinity. Can you guys think of when that might be true? It's not necessarily related to this problem, but I mean, not the radical axis, but the radical center of three circles, that is. So when does radical center of three circles not exist? Concentric circles. Well, if you just have two concentric circles, you already don't have a radical axis. Because, you know, like here, the power of point P with respect to the smaller circle is positive. The power of point P with respect to the larger circle is negative. So there is no, like, you know, the expression is like d squared minus r1 squared equals d squared minus r2 squared. Since they share the same center, because we said they're concentric circles, and since they're not, like, if they're distinct circles, r1 doesn't equal r2. So these two can never be the same if they're concentric. So yeah, I think these are two quadratic functions in D that have different so these are two quadratics in D that have different like y intercepts, so they'll never intersect, and they're similar parabolas. So yeah, here the radical axis of just two circles doesn't even exist. But let's say we have two circles that are not like that, right? So can anyone draw or say how to draw another radical axis that would be like not intersecting this? Same radical axis? Okay, that's, I mean, so that's also true. And then Adritis is parallel. Yeah, that's what I was getting at. But yeah, there's two possibilities, right? One possibility is all three circles have the same radical axis, right? This is called, like, I don't know if there's a name for this, maybe a pencil of circles. I recall reading that in EGMO vaguely, but there's also the case where they're distinct and parallel. So you could also have, like, instead of that, let's just redraw it. You could have this. You know, you could have this, and they don't have to be the same size circles. I'm just bad at drawing. So yeah, now you could have this be the radical axis of two circles, that be the radical axis of two circles, and then the third radical axis of the left and right circles is maybe somewhere like that. So now all three lines, they intersect at the point at infinity along the direction of this set of parallel lines. So you could say it doesn't exist, but most people say it's, you know, projectively, it's at the point at one of the points of infinity. So, you know, in projective geometry, for every set of parallel lines, you can associate a point at infinity with that set of parallel lines. So there's a point at infinity, which you can think of as infinitely far away in that direction. There's a point of infinity associated with these three parallel lines, which is infinitely far away in that direction, and so on. And all of those points of infinity form a line at infinity, just like, yeah. So, okay. So yeah, so that's, you know, parallel radical axes, or like all three circles share one radical axis. Okay, so those are just some configuration issues that, you know, is good to be aware about. Let's see. So maybe we can look at an AIME problem. I'll be right back. You can read it in the meantime. Yeah, they're not really configuration issues, just like special case, special configurations. Nah, whatever. So, so it might take a couple of tries to draw it accurately so that you can somehow fudge around the points so that C, Y, and D are collinear. But let's just say we already tried a few times and failed to draw it accurately, but now we have somewhat succeeded. So it says, let's see, we need to find AB squared. We're given the length of XC, XY, and XD. Okay. XC, XY, XD. So next says CB, XY, and yeah, so we can use the radical center theorem or the radical axis theorem, which says that the radical axis of these two, radical axis of these two, and radical axis of these two, they'll be concurrent. Let's say at point M or something. I guess it can be O or P or something. Let's just call it P. So we need to find AB squared. Okay, so I have not yet done this problem, but I'm sure it is probably one of those problems that is unsolvable without knowing the radical axis theorem. And it's solvable if you do know this theorem, which we have now used. So maybe I'll just label the stuff that was told. Ooh. One thing that I think, why do I think this? So let's try to solve it together. I think that PX is a symmedian of PAB and that Y is the midpoint of CD. But why should that be true? So, maybe we should just briefly, I don't know if we'll be using this in our final solution, but there's a concept of a symmedian. You have the regular median of a triangle, and then you have a symmedian of a triangle. So one way to construct the symmedian is to, so if you have the A symmedian, you draw the tangents to the circumcircle of ABC at B and C. You connect A with this point P, the intersection of the tangents at B and C. And this is called a symmedian, the A symmedian of ABC. The reason it's called that, well, it's the isogonal line of, or the isogonal of the median, meaning that these two lines, this line and this line, they are reflections of each other over the angle bisector of A. So if you draw the angle bisector, so this point M is the median, is the midpoint of BC. This is the midpoint of the arc. So I'll call it K. So the red line is the angle bisector of BAC. So basically I'm saying that these two angles are the same. So there's two ways to construct the symmedian. One is as the reflection of the median over the angle bisector from A. The other is with the tangent line construction, and you can prove that those are equivalent, like they give the same line. It looks like MKP are, well, yeah. So yeah, can anyone see why MK and P are collinear? Based on what I've said, it should be relatively clear. So prove MKP collinear. So M, I said, is midpoint. K is the intersection of the angle bisector of A with the circumcircle. So where is K along arc BC then? Yeah, it's halfway, right? K is midpoint of arc BC, the smaller arc BC. And then so this is just and then P is the intersection of the, like, you can draw this, the center O, P is the intersection of the tangents at B and C to the circumcircle of ABC. So yeah, all three just lie on this perpendicular bisector of BC. So this green line is the perpendicular bisector of BC. It passes through the center of those circle and like all three of those points. So I'll have to think about why the two constructions for this median are the same, but maybe I'll just write it down, right? So median equals isogonal reflection over angle bisector of the A median. So the symmedian from the vertex A is the angle bisector. Yeah. It's also equal to the like line joining A with the intersection of the tangents. I'll just denote the circumcircle of ABC with the parentheses ABC, like in EGMO. So yeah. We should definitely prove this fact, because symmedians are really important in Olympiad geometry, and we should probably prove this fact. But what I was just saying is that, like, I think PX is a symmedian of PAB, and C, like Y, is a median of PDC. like if one is true, the other is definitely true, because we have a cyclic quadrilateral, right? ABCD is cyclic. So I'll just mean the parentheses to say it's cyclic. Whenever you have a so you can think of, so whenever you have this configuration, so this is probably a good intuition to convey. Whenever you have a cyclic quad, like let's just draw the cyclic quad and so let's say I draw like some Chavians through A, right? Just any line through A. Then AX is basically the isogonal inside ABC. Let's call this P. Let's call this AD. So inside triangle PBC, PX is the isogonal of PAD inside triangle PAD, basically. Because if ABCD are cyclic, that means that you can kind of take like you can take this triangle and then you can reflect it over the angle bisector of P, and then you can enlarge it to get the other triangle. So what I mean by that is, let me draw it this time. So you can take this triangle, you can reflect this triangle over its angle bisector of P. So here's A and B, and then you reflect it over the angle bisector, so it becomes A prime and B prime, and then you can scale this A prime B prime to C and D. So there's a homotheity or dilation from PA prime B prime to like PCD. So these two are supposed to be parallel, and then if you do this construction, ABCD is cyclic. So here's a question: why is ABCD cyclic if you do this construction that I just described? So and this is one way to characterize like a cyclic quad where two of the opposite sides extend at a point and meet at a point P. So you can think of PAB being like reflected over the angle bisector of P, ABP, and then dilated it to CD. So that's how you transform PAB to CD. It's sort of anti-parallel. Yeah, that's the word for it. So PAB equals PCD. Yeah, so that's right. Yeah, Alan says this equals this, because I said that A gets reflected over to A prime and B gets reflected over to B prime over the angle bisector. So these two are at the least the same. And then you just dilate this green line to this red line. So these two are also the same. So that means the if this is alpha, this is and this is beta, then this is 180 I mean this is also alpha, so this is 180 minus alpha. So opposite angles add up to 180. Let me make it a bit less. Yeah, so this is also alpha. This is 180 minus alpha. So yeah, opposite angle at A and at C, those two angles are opposite in ABCD and they add up to 180. So ABCD is cyclic. And maybe we should prove that fact, but just for the sake of continuity, let's continue. So that means if what I suspect is true, if Y is actually, so if Y equals midpoint CD, then oh, I didn't finish explaining the isogonal line thing. So let's say I draw in this diagram, right? I draw the height from P to AD, right? Then I know that this line PY, it also contains the circumcenter of PO or PBC, because here are some isogonals that are good to know. So if you have a triangle, you have the height from A and you have the line to the circumcenter. So let's say that's the circumcenter. So, and then I'll just draw the angle bisector to see that it's like reflected over. So you can see that these are isogonal because if this is B, let's just call this angle B as well. This is 90 minus B. And then since, you know, we drew the circumcenter, we should probably draw this. This circumscribes that arc. So this central angle is 2 times B, angle B, ABC. If I cut it in half, you know, these are radii, circumradii. So this is 90. This is B and B. And so this is also 90 minus B. So then this part is half of angle A minus 90 minus B, and same for that part. So these are equal. You know, another way to say it is that these two are equal, which is equivalent. So it turns out that with the trig form of Chayva's theorem, you can prove that, like, you know, if you have 3 Chayvians in a whatchamacallit, in a triangle, then and they happen to concur, then their isogonal lines will also concur. So if I reflect, you know, this over it, the angle bisector of A, so the green line over the angle bisector of A, if I reflect this green line over the angle bisector of B to get this, and if I reflect, this is probably not going to work out very well, but, you know, let's just fudge it so it looks, and then if I reflect this green line over the angle bisector of C, you know, these 3 blue lines should actually intersect. So if the original point of concurrency is P, then the new point of concurrency P prime is called the isogonal conjugate of P. So in other words, the orthocenter where the 3 altitudes intersect, it's the isogonal conjugate of the circumcenter. Because you know, this altitude is also the isogonal line of this line, and this altitude is also the isogonal line of that line. And my these should be, you know, concurring at the orthocenter, and these 2 green lines are isogonals of each other. The reflections of the angle bisector of C. So with this, if you prove the existence of the orthocenter, you can prove the existence of the circumcenter at the same, like, stroke, kind of. Yeah, this case is a little weird because the Chayvian of the, like, the circumradius, it's kind of like, yeah, it's fine though. Okay, so basically the intuition that I was trying to explain was, you know, if you just in the cyclic quadrilateral thing, if you have, this is a cyclic quad, ABCD, and, you know, you have this configuration, they intersect at P like that, then, you know, if this is a median, like, let's say this is a median of CD, so M is the midpoint of CD, then P to, like, Y would be the symmedian of PAB, because yeah, if you drew in the median, well, it's because of this, you know, explanation that I gave here. If you drew in the median of PAB, so let's call this M2. M2 is PM2 is median of PAB, and PM1 is the median of PCD. Then these are going to be reflections over the, let's just erase this. These are reflections over the angle bisector of P. So that will be the angle bisector of P. And this is because of the, you know, the transformation I described earlier here. So I think we can get something about this AIME problem that is true. So I think this is true, but so let's just, I think there should be something interesting going on here, right? Because on the one hand, in the AIME problem, we have something like, oh no, what was it? It was the, it wasn't like that, but it's okay. So we have a tangent, and then these are 2 points of a cyclic quad. And then somehow the other points like the, so I just won't draw the third circle, just pretend this is a cyclic quadrilateral. So A, B, C, D is cyclic. And somehow CD is collinear with Y. So just these like interesting set of like occurrences, that there should be something special about this, right? Maybe it's the opposite of what I was thinking. So let's say you have this tangent. So this is a common lemma, right? So if you have a tangent AB, right, to 2 circles that intersect like this, and I draw XY, the radical axis, then yeah, can anyone see where M should be along AB? M is midpoint of AB. Yeah, why is M the midpoint? So let's see. What theorem should we use? Which I guess we've been using all day today. MA squared equals MB squared from radical axis. Okay, yeah, that's true. We don't even need the constant of radical axis. We just need power of a point. So MA times MA is MX times MY. But MX times MY, that's the expression for the power of M with respect to both of these circles, right? So that's MB times MB. So because MA and MB are not negative in numbers, they're both positive. So MA equals MB. So that equals that. So in our original AIME problem, yeah, power of a point. So in our original AIME problem, that means this point is the midpoint. Let's just call it M of AB, which means that P to Y is a symmedian of PCD. I also think that there might be a cyclic quadrilateral here, like PAXB might be cyclic, but see, would that always be true? So we know that, let's see. So we know that by the radical axis theorem, these 3 intersect that are concurrent at the same point. We call it P. So is this actually cyclic? Or is it not cyclic? I'm not sure. Maybe let's just draw it in dotted like this. The more I do these classes, the more I realize that colored pencils might not be a bad idea for doing Olympiad geometry. I never did that as a student, but it seems, reasonable to use colored pencils. I'm also not sure if dx is collinear with b or not. Same for cx. Is it collinear with a? Probably not, but if we actually do the AIME problem, we were given some lengths like 37, 47, and 67. And now we know a midpoint exists. I don't know if the red dotted circle is actually a like if those points are actually cyclic or not. We So the fact we're not using yet is that somehow these 4 points are cyclic. And we also need to use that CYD are collinear. So yeah, A, B, C, D being cyclic, and maybe we should mark some equal angles, like this is equal to this. This is equal to that. So we should probably also, so if we draw in this line, because angle C, the purple angle at C, because CYXB is cyclic, then this is also the purple angle, right? Because if this is alpha, this is 180 minus alpha, and then the outside angle, the exterior angle at X to the cyclic quad CYXB is also equal to alpha. So that means that what I said is true. So PXB as an angle equals angle PAB, which is sufficient to prove that the red dotted circle is actually, so that means like PAXB is cyclic. So that's all on a circle. Okay. So then we can use power of point on some other things like M. Like for instance, M is now the radical, M is the radical axis of this red circle, omega-3, and this omega-4, right? I mean, M is on the radical. So AB is that radical axis of omega-3 and omega-4. So, I don't know if this is helpful, but on the one hand, MA times MB, which is just MA squared, is MX times MP. And it's also, oh, we don't have that even on the, so if we label the red circle intersection with PX, it'd be like M that point to MY. But now we have 2 distinct points here, which may be relevant, but the top one is M, by the way. So maybe I'll label, this one is M. This one I'll just erase. So we have 4 cyclic quads. We should be able to do something with that. One thing, oh no, hang on. So maybe I should label this with the purple angle too. This is also. And then, oh, actually, we don't know that yet. We haven't proven that DXB are collinear. So we don't know that yet. Similar triangles with AXB. Which triangle is similar to AXB? So let me just write down so I don't forget. We don't know if DXB collinear. It would probably be good to give a notation for that in my work. So I'll just put an overline over it. But at the very least, we know this is also the orange angle. And what else can we conclude is the orange angle? Let's see. We should probably just draw in. I've been hesitating to draw these in, but I think it might be good to draw these in. So AXB is similar to DXB. AXB, AXB, PX. Oh, somehow I misread that. PXC. So AXB, I'm not sure how you're getting that. So let's see. So I know that at the very least, XAB equals XPC. So they share this angle. But then what about the other two angles? I don't know if AXC are collinear, so I'm not, hang on. XBA equals XBC. XBA is XBC. Okay, by the tangent, right? Yeah, I see. So XBA equals XCB by the tangent. Okay. Yeah, so we have a spiral similarity centered at X that takes XAB to XPC. So we'll just say XAB is similar to XPC because of angle-angle similarity. So that is. And then we have the same thing on the other side, I guess. So XAB should also be similar to D or XDP. So similar XDP by the same reasoning. Because this is a shared red angle with that, and this equals to, well, that's just the purple thing, so I'll just do it in purple with the cross through it. So we have a set of three triangles that are all similar. PBC are collinear because, hang on, PBC are collinear. So PAB we can find XP and then try power of point on M. Okay, let's see. Yeah, that's true. So XP is using the outer two similar triangles. I guess XP should be, so XP is 237 as XP. So this is true. So XP is root 37 times 67. And then let's see, try power of a point on M. Let's see. With respect to three circles, AXBB, AXYD, AXYD. Okay. on bx yc. That times that equals that times that equals that times that. Okay. So let's just scroll down a bit. So I'm not really sure that. I'm not sure that M should be used for the power of a point to like the top two black circles, dy xa and cy xb. But maybe, because we've already used that information for the most part. I think one thing that might be good to use is, so because of the cyclic quads, this angle at D also equals this angle at Y. And this angle at C also equals this angle at Y, the other angle at Y. So by angle-angle similarity, we should have these following similar triangles. So DXP, YAP. And then CXP, YBP. Maybe that can be helpful. So then this equals this, but then that also, oh, okay, that's the same thing. So we just needed AB squared, right? Let's just bring down the problem once more. Yeah, find AB squared. AB squared is 4AM squared. Okay, so we just need the power of M with respect to two of the original circles, right? So 4AM squared equals, so it suffices to find the power of M with respect to like omega 1 or something. this, let's say that's omega 1. So we just need this length, like mx. Need mx. 4 times mx times my. Yeah. So need 4 mx my. Yeah, I guess it's good to work backwards since I'm a bit stuck working forwards. So if I can find mx, that's fine. So that's the same as finding mp, right? So we just need the length of the median in PAB as a triangle. Because if I know because we already know xp was this. If I can get mp, so need mp, then that's good enough. Okay, yeah, so we should look at power of a point with respect to m, I guess. So let's say mx is little x. Let me just copy this down because I'm running out of space and I don't want to redraw this. So mx equals little x. K equals this is px. So mp is k minus x. There should be something nice with the similar triangles. Let's see. So what have we not used yet? Have we used the fact that CD and Y are collinear? Maybe we should use that. So maybe I'll just call this, I'll call the angle dyx. Dyx is gamma. Now let's call it a theta. So that's theta, which means that this is theta. So angle that equals angle CBX. And what else is theta? That's theta equals angle PAX. Okay, we already kind of used that to prove the. How did we get that? So need use CYD collinear somehow. So we have a median and we have a symmedian. I don't know if we need to actually use facts about the symmedian. So I think there is maybe we should look at XCD. I think XCD is a good triangle to look at. So XCD, we know like, so let's just draw it separately. So we know this is 37, this is 47, and this is 67. This is X, this is Y, this is C, this is D in the diagram above. And so you can probably get some fact about so we know that like, so we also have this is P. So because PX is a median of PAB, so PY is a symmedian of CD. So we can get the ratio dy to YC. Is Y the midpoint of CD? Yeah, Y is not the midpoint of CD. It's the symmedian point. I mean, it's not the symmedian point. It's like, so you know, I said that PX is median of triangle APAB, which means that PY, which is the same line as PX, is the symmedian of PCD. But so in other words, what that means is, you know, if you draw like the circumcircle of PBC, the two tangents, you know, meet at like this point. But I kind of doubt we'll be using that. The other thing about the symmedian is that it's when you reflect it over the angle bisector of P or CPD, you know, then this becomes the median of CD. But I drew that very horribly out of scale. I think there is a fact you can prove about symmedians and just reflecting over the angle bisector in general. So we should be able to find CY to YD, or, oh, but we don't know, we don't know PD to PC though. Okay. So another question that's natural to wonder is, what kind of Chavian is this thing inside CXD? Is that also a symmedian in this triangle? Finding the ratio of CY to YD would be useful, since then we can use Stewart's. Yeah. See, this is why I always like didn't do AIME 15s when I was a student. I did early Olympiad problems instead because, well, this is basically Olympiad flavored, but just the style of late AIME problems, I'm worse at that style than early Olympiad. But here it's kind of indistinguishable. The style is the same from earlier or mid Olympiad even. So let's see. That angle equals that angle. Oh, okay, I see. So I think, oh no, is that even? So I have this hunch that, so I think that DXB and CYXA, these are collinear. And I think that this point X is actually the symmedian point of triangle PCD. So I haven't said what a symmedian point is, but basically it's the intersection of the three symmedians of the triangle. So it's the isogonal conjugate of the centroid. So if you draw the circumcircle of ABC and you draw these tangent lines, this is the A symmedian of the triangle ABC. You draw this tangent line and this tangent line. This is the B symmedian of, let's just call this like K, J, and L or something. And then you do the same thing here. So this line CL is the C symmedian. So C symmedian. And the three symmedians here, they meet at the symmedian point of ABC. That's the symmedian point. Maybe the letter is like K or something. Symmedian point. So I think that's the special point in our diagram, actually. C symmedian CL. So there was this, so ABC is the end center. Yeah. So I guess, K is also the, well, this is a right angle, right? Because these were like, oh, no, that's not, yeah. That's not. That would be if you drew the instance, the center of the circle. Wait, isn't K also the intersection of LB and JC? Oh, okay, yeah, sorry. The reason I put K, so maybe this is why they don't label this way. Let's just call this I. I think, like, you know how H is often the orthocenter, O is often the circumcircle? I think there should be an, I forget if it's L or K, maybe it's L is the common letter for the symmedian point, which is a triangle center of ABC. Maybe but I used L here as well. So K or L, one of those is like the standard, letter for the symmedian point. So I think that X is actually the symmedian point. And it might be that XD, so it might be that like these are collinear, XDB and XAC. The reason that I know that X is the symmedian point, I think this exact configuration showed up on 2009. Yeah, let's see. Maybe I can find the problem. But there was this US AMO problem where if you had there was this US AMO problem where if you had X, so I don't remember the exact year, but basically it said that if you have this configuration and this triangle is similar to that triangle in the order of like PAB is similar to PBC, then and there was one other condition, but so PAB is similar to PBC as a triangle, then P is the symmedian point if we know that this is also a symmedian line from B. Whoops, that should be on top of there. So it must have been 2008 US AMO or something. I don't really remember, but let's just look up 2008 US AMO. I'm not one of those people who like memorizes the exact like problems of the exact year of the exact like on a certain test, but yeah, basically if you know the result from this problem, then you can kind of conclude that P is the symmedian point of the triangle in this. Yeah, this was 2008 US AMO number 2. If you know like the configuration from this problem, then I'm pretty sure you can conclude that this point X is the symmedian point of P of triangle PBC, like here that I wrote here. The US AMO problem was proposed by Zooming. Okay. Yeah, I don't know. I remember reading the thread for that problem and looking at a lot of the solutions for that problem. So if we go with that, so this implies P is Simidian point of ABC. If we also know that, for instance, PB is Simidian line. So both of these imply, you need both together to make that conclusion. So there's probably some projective geometry fact that would be useful here that I am not familiar with. So let's see. So we should mark some of these angles as equal again. So I know this angle, let's just call this alpha, is equal to this angle. Let's ignore the big purple alpha for now. So I'll just erase that. Oh, no, I can't erase it. So we'll just ignore that. Okay, if you have to go, no worries. We'll probably end in a few minutes too anyways. I don't know if we'll finish the problem, but it's a good problem solving session. So let's see. And we said that this was equal to XBA, and it was also equal to this angle. This is also alpha. So let's see, can we get anything? Similarly, if this is beta, this was also beta. And what? That's also beta? The heck? So that means that we have some parallel lines. Is that even true? I feel like this is too good to be true. And this, I don't know if this is, because on the one hand, we have that this is alpha. It makes an alpha angle with this PY. And on the other hand, oh no, this is big. On the other hand, this is alpha and it makes like this angle with PY. So that must mean that BY is parallel to PD. So let's write that down. BY parallel to PD. Hopefully I didn't mess up any of my reasoning to conclude this, and AY parallel to PC by the same reasoning. Okay, that's huge. So we have some, similar triangles. Okay. It's still very awkward to deal with the given lengths, but this is huge. This seems, I don't know how, I guess that's true. I'll probably, So it's getting pretty late, so I might just end it here. But hopefully, there should be enough information, I feel, to extract the answer from here. Basically what we have is we have a Simidian line, and we have two parallel lines from this base of that Simidian line. So, you have like PCD, you draw the Simidian of PCD, and then you draw a parallel line to here and a parallel line to there. The problem is that this point X is like, we're given these three lengths, which are kind of awkward to work with, but I mean, that's just what we have. And then this is Y. And then, yeah, so Y to, let's just call this point M. YM is both a median in ABY, and PM is also the same line as a median in PAB. So maybe that can be useful. But and I know from that other USAML problem that X is the Simidian point, I think, of so there should be, you should be able to compute the ratio of this angle to that angle, or the ratio of the sines of those two angles, if it's actually the Simidian point. The problem is we don't actually know any of the side lengths of PCD, so that's kind of annoying. I think one thing that is true, maybe I'll just end like this because it seems like it might be relevant, is if you have a Simidian line from A to line BC, then I think it's true that like if this is C and this is B, and this is X and this is Y, let's just call this Y and this X. So X to Y, I think, is B squared over C squared. If AL is a Simidian line. So that means that if we knew that the ratio of this to this, then we can figure out the ratio of that to that. The problem is we don't know that. It might also be true that this is a Simidian line of XDC, but I'm not really sure. Yeah. Let's see, how do you prove that? Yeah, these are some proofs that I have not repeatedly gone over myself and can't recall or don't know. But yeah, in general, there is a general formula for like how an isogonal line cuts the other side. If you know how the original line cuts the other opposite side BC from A. So yeah, maybe we'll just stop here for today. It's unfortunate that we didn't finish solving the problem. But yeah, thanks for everyone for coming and helping me look at this after I lectured on like radical axis and stuff. I think this is one of those AIME problems where you have to know radical axis and else there's no hope, because then you don't even know if P is a single point. But we do know by radical axis that P is a single point, so that's good. I'll share the PDF with everyone so you can just have it as a reference in case you want to keep working on it. But I should really get going, and it's late for Eastern time people as well. Okay, bye.